Jaden, we are going live. And we're live.
Awesome. Okay. Well, welcome back, everybody. It's been a while.
Yeah, it has. I hope you guys had a great Christmas holiday break and enjoyed yourselves. Because school
Yeah.
sucks, am I right?
uh, sometimes. Sometimes it's nice. But just want to say thank you to everyone that watched the Christmas special and that donated, and we really appreciate it.
Yeah, we really
We
do.
already have a comment in the chat.
Says, I read today that the reason why there is equilibrium between objects and that the Earth's surface is that the gravity of each object neutralizes the other. Neutralizes
Neutralizes
the
the
other.
other.
Is this true? The answer to that is yes. Nick, if you would like to elaborate a little more, I think I understand what it is you're asking. But I think that has to do with Newton's laws, and that for every force there's an equal and opposite force.
Right.
Is that what you're getting out of that, Jaden? So I guess
Uh, yeah. Would
I
you elaborate just a little bit more? But I'm thinking that, right? If you're pushing on a wall, you're not going to move the wall because the wall is pushing back at the same force you're pushing the wall. Uh, but if you move like a ball, right, that is obviously a different structure, but it still has a force on you. I am
right.
pulling up on the Earth's surface enough to not get squished. What's pulling me away from the Earth?
Well, nothing's pulling you away from the Earth. Okay, here we go. So I'm drawing a beautiful world here, and here's Nick. This is to scale. I think Nick is a massive human. So this is to scale.
To scale, definitely. Yeah.
Okay, so to go through this, um, gravity is pulling down on Nick, right? And it's pushing him to the
Right.
center of the Earth. So Nick's question is, why is he not automatically being squished? Um, so Nick, you have these things called
That.
legs, right? And your
Right.
legs are very strong. So if this is the Earth. So we're going to do a profile view here, and we're going to just draw a flat Earth here. The Earth isn't flat, but when
See,
you zoom in close enough, it looks flat.
this is for all the flat earthers out there.
Yeah.
Here,
So
I'll
if we,
draw a little
oh,
like. Here's the other part of the Earth. It's flat, right?
no. So if we,
There's a little waterfall. Whee!
it's under the dome
Okay.
too. And did you know I have like the Flat Earth Bible and I've been reading it. There's actually more sea up above us here, just in case anyone's wondering. Um,
Oh wow. Okay.
okay.
I'm glad you cleared that up for us.
Yeah. Okay, so we've got Nick, gravity's pulling Nick down this way, right? And Nick, you're getting squished, or not really getting squished, but what's happening is the Earth wants to pull you down, right? It wants to pull you to its center. But there's a problem. There's material in the way. There's mass in the way. So you're on the Earth's surface, and so the Earth is stopping you from going down any further. But at the Earth's surface, what's happening is so your body's pushing down into the Earth because gravity's pulling you down in, but the Earth is pushing back up on you. And so your legs are taking that weight or that force because
And
weight
Chip,
is the
what is that force called that's pushing back up against everybody that's standing on the earth.
That is called the normal force, Jaden.
Cool. And so this is Newton's third law, right? Where everything has the equal and opposite
Right.
reaction, right? So
Right. So for
okay.
so in this case, the Earth, we're pushing down on the Earth, and the Earth is pushing back on us. And so in this case, Nick, your weight of your whole body is on the surface of the Earth. And I'm just going to simplify and turn it into a box here. So, well, actually, I'm trying to think here. But your legs, I'm trying to think how to visualize this and draw it out. But your legs are actually what are keeping you up. So there's a force from your legs.
So another question is, why aren't we exploding, right? Because there's a force inside our body that's pushing outwards. So that's another question that we can maybe expand on after we finish this one.
Yeah, and we also have another question that says, what causes the normal force? And that's from Kelsey, so we'll dive into this a little more here.
Okay.
All right, so I'm going to simplify even more, and we're going to just say that we have the Earth, and we've got a box, okay? So this box is being pushed down, and I'm going to give this an FG, right? So that's called the force of gravity, which the force of gravity is equal to the weight, okay? So force of gravity is equal to the weight of the object. So when you weigh, 130, 40, whatever pounds, 180 pounds, that's your force of gravity, all right? And then, so the question is what causes the normal force? And it's just simply I don't know how detailed we want to get into it, but it's the idea that there's simply, there's another object in the way, right? So this Earth surface is right here, and so the Earth's surface doesn't want you to go through it, right? The matter doesn't allow you to pass through matter, right? And so it's stopping you. And if the Earth's surface was weak enough and it didn't have a strong enough normal force to push you back up, you would actually slowly fall through the Earth because you'd be stronger than the normal force, and you'd be slowly getting sucked down to the center of the Earth.
That's like tunneling, right? If you could magically walk through a wall, have every single one of your atoms and particles just magically fit through the wall's particles, that would be pretty nifty.
We got a science
perfect puzzle piece.
Yeah, we have a Bill Nye the Science Guy joke reference here. It says, "So this is why we need to eat our crust." If you remember, there's I don't know if you ever saw that.
So this is why, yes.
Yes, exactly. And then Nick, we've got a question from Nick saying the rigidity of the Earth exerts force. So right now it's winter time, right? And if you go out into the snow, not that we have a lot of it right now, but if you do go out into the snow right now, if the snow is soft, right, you'll just step on the snow and you'll go straight through, right? You'll just fall through the snow.
Right.
And that's because the snow isn't dense enough or strong enough or whatever, the molecular structure of the snow isn't strong enough to hold up your weight, so it breaks away out of the way and you fall through the snow until you get to either compact the snow enough or get to a hard enough, dense enough layer. But that snow is still exerting a force back on you but it's just not strong enough to stop you from falling through the snow, right? Is
Yeah,
that a
I like
fair
that. Yeah.
assumption? Um,
Um, the atmosphere is very important for our bodies also, not just because we need the oxygen to breathe, but just having an atmosphere makes it so our body doesn't explode itself also, because inside of our bodies we have forces in every direction, right? uh, and if we didn't have the atmosphere pushing on us in every direction, we could explode. And that is why we have special spacesuits for astronauts, because that helps them to, one, breathe in space, and two, not explode in space. So that's
exactly.
another important thing about the Earth and staying alive.
That is great. Thanks, Jaden.
Yeah. We have a comment. I love normal force, especially the snow example. Shows how normal force is variable based on density of matter. That works exactly with like water also, right? If you are thinking you're going to walk on water, think again,
Right.
you're going to
It,
fall right through it.
yeah, exactly. So I've got a new slide open here. And
I have another question,
oh,
comment. Sorry, Kip. Uh, it says,
why?
why does ice float? That is a great question, right? Solids generally are more dense than their liquid form. Water is a very special, like, example that is not more dense. When water freezes, it has a special structure. The molecular structure forms crystals instead of like compact solid that we usually have. I don't know, Kip, do you want to try explain that a little better?
Sure. So I think what they're trying to get at here is how does density kind of affect things, right? Because now we got bugs walk on water all the time. And if you're a fan of Lord of the Rings and elves and stuff, you know elves can run on top of the snow without any problems. If you go out skiing or snowshoeing,
They
all
have
of a sudden,
magical snowshoes.
I don't know, maybe elves have less dense bones than we do. Um,
Yeah.
so the um, or who knows, dude? They cast magical spells. Maybe it's density related. So we can go into
Yeah.
density really quick here. But the idea behind density, in the examples that we've been giving so far, we've been talking about essentially a point mass, right? So you have a circle, and this is just what?
That's a good circle.
Thanks. I'm going to art school if you can't tell. And so
Dude, modern art.
the circle is taking all the weight and putting it like straight through in a you know what, Jaden? Your circle's way too big.
It's
I'm
a
trying to
big
make
snowball.
I'm trying to make a point here, like literally a point and also a point about density, but um
Okay, continue.
okay. So what we've been talking about so far is if all the mass of the object was at a single infinitesimal, anyway, super small point. Jen, you can say that
Hard
word?
word.
That's a hard word.
Dude, I'm not even gonna try because I just laughed at you.
So it's all focused on a really small point. But when you take in density into account, density is the mass spread out over a certain volume of the object. So in 2D space, if we have a line like this, and this is our snow. Okay.
Okay.
And then we put a person on skis. Okay. Woohoo! And now he's got some big
Woo!
skis on, dude. Look at those. Those are some big skis. Now, Jaden.
Wow, I don't think he's gonna fall through the snow
But why not?
because his mass is spread out over a greater surface area.
Exactly. So now, instead of having all of his weight at one point directly underneath him, his weight is spread out evenly across here. And so what it becomes is it becomes essentially an equation of density, where if he's more dense than the snow, he's going to fall through the snow. But if he's at the same density as the snow, he won't fall through it, right?
Right.
And so that's density is, it's the amount of mass per unit area. And so or per unit volume, so the more you spread him out, the less dense essentially he becomes over the snow. Does that answer the question that people were looking for? If not, let us know and we can dive into it a little more.
But bugs are pretty cool. Those water skeeters just skeeting across the water.
Yeah.
Lucky guys.
Lucky guys. And there's also a great episode of Mythbusters if you ever want to watch people try to run on water. It's pretty funny, but yeah. So why do the salt crystals in the Great Salt Lake float until they are touched or disturbed? That is a great question, and I think that has less to do about density and maybe more with, I'm not sure.
I don't know what the salt crystals are exactly. I haven't been to the Great Salt Lake enough to experience that.
So in the Great Salt Lake, Jaden.
There's also, so you could, if you wanted, you could right now grab a glass of water and a paper clip and make it float, right? This is a chemistry thing. It's called hydrogen bonds. Hydrogen bonds are really strong, and they can, like, actually lift things up if you don't disturb them enough. So if you're very gentle and put that paper clip on top of the glass of water, it can, like, float. It doesn't mean it's less dense. That's just, that could be something with those salt crystals.
So
I don't know though.
We've got this question that is discuss surface tension of water, which is kind of what going for there.
The hydrogen bonds.
Yeah. To be honest with you, I understand the brief concept of surface tension, but I don't feel like I have enough knowledge to dive into it and not sound like an idiot. So that one we will keep for next time, and we will look into it more. But that's starting to get a little more along the lines of chemistry, and we do hydrogen physics and math here.
Hydrogen bond, like James Bond.
Yeah, not bombs. Yeah. Hydrogen bombs are very heavy and very dense.
Yeah. They'll make water go boom boom.
Cool.
We should do the paperclip thing and show us. I don't know if I have a paperclip.
I don't have a paperclip or a glass of water.
We'll do this next time.
Next time. Stay tuned for next time when we discuss surface tension. Cool. Also,
thank you for all the questions.
Yeah, thank you guys. If you haven't subscribed, you should go ahead and hit the subscribe button, by the way, because we have this cool new animation that pops up when someone subscribes.
Oh, yeah.
Also, I think that there's some magic that's happened, so here we go.
Yes, I agree.
Okay.
And if you are liking the stream and getting some questions answered and having a good time, go ahead and hit that like button.
Yeah, smash that like. Oh, and share with all your friends and family. Get us popular. Because that's all we ever wanted to be in life, was popular.
That's every waking moment is just thinking about being popular, right?
Right.
Right, Kip?
Right, Jaden. That's life.
That's life. Okay, new slide.
Okay.
Okay, Kip, what we're going to talk about, we kind of got a lot of good questions tonight, and we went on a little bit of tangents here and there, talking about James Bond a little bit. What originally were we going to talk about today?
I think we were going to talk about radicals. And if you want to start off, also if anyone has any math questions for their homework, they can do that. Also, we have a
Oh,
comment
yeah.
from Kelsey saying nothing happened when I subscribed, and that would be a bummer if that's true. Kelsey, did you actually hit the subscribe, or have you already subscribed before? Because I feel like you were already subscribed, and it won't do anything if you already subscribed. So, it's only
We
for
have a
new
couple
subscribers.
pogs in the chat.
We also have a comment from Jason Quinn and from Jake Quilter, both saying POG. I am not sure what POG means. If they want to elaborate, I would appreciate it. I don't know the hip young lingo of the day.
Okay. Well, while they elaborate, I am going to start on the radical adventure. So, for those of you that don't know, sometimes at the beginning of the streams, we do a little lesson just for those that want to learn math that they've never learned before or want a good refresher in math. Last time we were talking about exponents, and naturally, what follows exponents is radicals. The reason why radicals and follow exponents is because they are the inverse of the exponent. Let me clarify real quick. If we have a squared, to basically undo a square is to do the square root. This symbol here, the square root symbol, is called a radical. And that would just give us an x. If we are in the positive real numbers, right? We could also get a plus or minus sign, but we might talk about that tonight. What do you think, Kip?
Yeah, I think we should go into that. But
Okay.
we'll have to go
So,
into why and when it's a plus or minus only.
okay, let's do an example then, right? If we have the square root of 2, we all know that would be 4. So then if we take the square root of 4, we would get 2, but we would also get a negative 2.
But
Right?
why,
Because,
Jaden?
why do we get the negative? That is a great question. Let's just do a quick mental math, everyone together. Negative 2 times negative 2. What does that equal, Kip?
Sorry, Jaden, you went away for a second. That equals 4.
4. Okay, so that was just a quick example, right? And 2, oh, you were going to write it. And 2 times 2 also equals 4. So with these radicals,
Dude, guess what? That is mathematical.
That is mathematical. We get, as long as our domain is not restricted, we get two values for radicals. The
Jaden,
negative
what is
and the
a
positive.
restricted domain? You're throwing out some
So,
fancy terms here.
okay, so a domain, that is basically the area of numbers that you want to work with, right? We could work with all of the numbers, and that would be, I guess, the complex domain, right? If you want to deal with every single possibility, we'd be in the complex. If you want to restrict that to just positive integers, right? That would be your 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. You could have a domain with your negative integers with your positive integers. So all the integers could be a domain. Um, does that kind of clarify what a domain is?
Yes, it does. Thank you.
Okay. All right. So exponents, like we know, they can be any number, right? We can have an x cubed. Kip, what would the, I guess, inverse of this cubed be with a radical?
Ooh, so
You
the
want you
inverse,
want to write
Jaden,
that down for us?
yeah, will be
Yeah.
x like this, and then we put a 3 out like that. Okay?
Okay. So what you just showed us, right? I guess any number we have here, I'll just represent it with an n, another variable. The inverse of that would be the radical symbol with the number right here,
Right.
correct?
And
Okay.
then there's another way to show it as well, okay?
Ooh, yes.
Which we can write it as a fraction of an exponent. So this equals x to the 1 over n as well.
Okay.
Okay.
So, Kip, what's the benefit of writing it one way or the other?
So the benefit, um, I mean, I personally like it in the fraction notation more, and I feel like the higher you get into math, the more you see fractions, unless you see the radical sign, unless it's
Okay.
a square root. Normally, I think that this notation kind of messy for a lot of people, and this notation is kind of easier for people to understand. The other reason why it becomes helpful is if we have, say, x squared, right, and we take the radical of that, the the
The
cube
cube
root,
root.
this
Okay.
also equals x to the 2/3. And so you can kind of get this
Oh.
visual representation of what's happening. And so if let's say that this wasn't actually, let's just say that this was a square root, then this would be over 2. And this part up here, we haven't really talked a lot about fractions, but these fractions would
Okay.
actually cancel each other out, and you'd just be left with x to the 1, which is the same as x.
Okay.
So
Cool.
that,
So
yeah,
the fraction representation can be, I guess for myself, it is a lot easier to use, especially in higher math like calculus. Uh, Calculus, you run into derivatives, and taking the derivative of one of these would be a lot easier than dealing with the radical sign.
exactly. And it's
So
something that, again, when you get into calculus, I think in particular, seeing a square root sign can be really daunting and terrifying, and you'll be like, how do I take a derivative of a square root? And then you go, oh yeah, it's just x to the 1/2, and then all of a sudden life becomes a lot easier.
nice.
Nice. But we're a long ways off from getting to derivatives in this course, I think.
Yeah, probably right. Some people might be able to understand it, but yeah, we're not there yet.
We are not there yet. Okay. The other thing, Jaden, that we've been doing so far is we've been kind of showing how it's the next step, right? So if you remember when we did exponents, we showed that it was a multiplication of the same thing over and over. So do you want to see if you can figure out and talk about how it's like the opposite of, I guess, division in a sense?
Right.
It's
Let's
a
see.
little
We
harder to
wanna.
grasp, I think.
Yeah, I'm trying to think of a good example. Would our one factory and the circles work
I'm
out in this
thinking it
example?
might possibly work.
Yeah.
I'm just trying to think how. And this is why it's good for us to think through this too, because it actually makes us think about what a radical actually means as well.
Right.
So let's refresh really quick just to get our brains going what an exponent means, right? So if we have a circle, 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 and circle, 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 that's 9, which is 3 squared. So how did we pull this off with our circles?
We need to go watch our videos, Kip.
I know. We do.
Let's see. So that's 3. Then we did boxes, right? Boop, boop. We were like, oh, that's gonna be
But
a
that was for
3
the
times.
multiplication. So
Yeah.
there was something about we had 3 boxes, or we had 2 boxes of 3 times 3.
Well, the exponent means multiplication, right?
Right. So we have 3
So that means we have
times
a 3 times
3.
3.
Uh-oh,
Okay.
we got an email question.
Ooh.
Let's see what it is and see if it's important to go through right now, if we should wait till after this. If you have an average shower pressure in the US, how long can you shower until you've used enough water to fill a bathtub? Whew.
That might be a question for next time.
Maybe. I think we can
We could probably answer it.
answer it, but Kelsey, stay tuned. We're gonna finish talking about radicals and then we'll go to your question.
Okay, so here we have a 3 times 3, that equals a 3 squared.
Mm-hmm.
Right. Okay, and we're saying the opposite of multiplication, the inverse of multiplication is division. So this would look like a 9 divided by 3 equals 3.
So, I think, Jaden, the way we have to do this, and this is where it gets harder, and I think it's why it's harder for people to understand. When you take a square or you take a square root, in the case of taking a radical, you're dividing something into equal parts, right? So it's an equal number of chunks, I think, and so this is going off the top of my head. Okay, so let's say we have 1, 2, 3. Alright, we'll do it like this. So we are going to have 9 of these circles, okay? Boop, boop, boop,
Okay.
boop, boop. Okay. And then, how are we going to do this? So,
Okay. I like this.
yeah,
So if you're doing, we can look at it kind of like a multiplication table,
okay.
right? So we have 3 and we have 3, right? That
Right.
is 3 squared.
Right.
Okay. So to do the square root, right, we kind of have to visualize it this way. Huh. How would we?
I don't know. Maybe we needed to think about this one a little more before we jumped into it.
Yeah, to actually like draw pictures and visualize it, it's hard. Let's see, do we have a what am I doing?
Um,
I think okay, so let's think about it with just the exponent of 2 right now, right? Squared. We can actually think of squares, okay? And I guess you'd have some side length x, and if this is actual square, then we know that every side length is x,
right.
okay? We'd know the area would be x times x, right? Or x squared, okay?
Right.
Uh, the square root would be the side length of the area, okay? So we know the side length is x, which is the square root of x squared that equals x. So if we think about it as this square, the area of the square is the exponent of 2, right? The side length to the exponent of 2. And then to get the side length, if you have an area of a square, you can just take the square root of it. Okay, so that works with the exponent of 2. The tricky part is expanding that to more exponents to visualize it.
Right. Well, Jaden, I think what you just did, which is pretty neato, is you just explained
Uh-huh.
why we call it a square and why we call it a square root. Look at that.
Oh, yeah.
That's it.
Cool.
Now we know why it's called a squared. We'll get more into the visualization, I think, next time. Um, but we do have a comment from Kelsey that I'm trying to understand. It says, I always just picture a carrot with square roots, if that helps. I don't know what that means, Kelsey. I'm sorry. I have no idea what you're trying to say. I'm picturing this.
Is your carrot like a magic wand and you just
I'm picturing this.
I don't know. Yeah, I don't know what that means.
No, but I think that this is important that we do think about this a little more and maybe get back to it at some point, maybe next time, and the visual
Yeah,
and the actual understanding of it, because I think that this is what part of my point is that we get into more and more complex math. We know how to do it, but actually visualizing and thinking through what it actually means, we
right.
lose sight of it, and we just tend to we know how to do it because we were taught it in math, but the actual physical concept, because again, math is a language that describes what's actually happening in our world around us, or it's not, or things that we don't see or whatever, but math is an explanation, so it's important to kind of remember what it
I was
actually
just
is.
I was just thinking of exponents, and that exponents are kind of like in this square situation, it's the dimension that you're in. So a square
Uh-huh.
is a 2-dimensional shape. If we do a cube, that's a 3-dimensional shape and an exponent of 3. And I guess to undo the dimension, you just get to a 1 dimension. And in these situations, it would just be the side length. And I don't know about you, Kip, but I can't like actually visualize anything higher than like the third dimension.
Why, Jaden? Where you can't visualize dimensions outside of your being?
Yeah, it's kind of difficult to comprehend, but in that sense, right? Every dimension higher than like a cube. So like if you have some sort of four-dimensional object that uses like a square, I don't know what that would look like, but that square root or I guess the radical, would, I guess, get you back to one dimension. If I'm thinking through this right in my head. I don't know.
Yeah, I think you're right. I'm gonna go one more page and I'm gonna quickly think. I'm gonna take it and okay. So really quickly, right? If we remember,
Okay.
3 times 3 equals 3 plus 3 plus 3, right?
Right.
So it's 3 times, right? So let's go
Yeah.
ahead and let's see if we can think about this in reverse, which this also equals 3 squared, which equals 9, right? So
Yeah.
if we wanted to take the square root of 9, let's see if we can work backwards here doing this. So 9 equals, like we said, 3 plus 3 plus 3, which equals 9 times, well, this isn't true. Sorry, hold on. Okay, so
You need the radical here.
yeah, okay.
But I kind
I
of
think
see where
I
you're
know
going.
where I'm going wrong here. So if we work our way backwards, right? So if we do square root of 9, this equals, if we think about it, it's going to be 3 divided, or gosh, how do we, okay, I'm getting there, Jaden, I'm getting there.
You are.
So we can write it as x times x, wait a second, hold on. Okay, I'm going to get rid of this radical. No, I'm going to do this. I'm going to radicalize both sides. Okay. And so the radical, okay, here we go. Jane, I'm on to it. Ready? Here we go.
Okay.
Okay, I'm going to say that this is equal to x, all right? And then from there,
Okay.
we're going to say that 9 is equal to x times x, right? And from there, we're going to say that x is equal to 9 divided by x, which is going to be equal to the square root of 9. So this is why I think this is such a tricky thing, and why we have to use calculators to figure out what radicals are. Because there's not a way to solve this equation without having to think through it, right? But what it's saying is that whatever you divide that number by, it's going to equal that number. And that's for a squared, right? So you have to break it into groups. Now, if we wanted to say that, you know, it was 9 is equal to x times x, then you would get the same thing. You would get the radical of, or this is equal to x, which is equal to, we'd get that is also equal to 9 divided by x squared equals x, right?
Yeah.
So this is why it's tricky, is because you have to, there isn't an easy way to really visualize that. But what you're doing is you're breaking it down into equal parts, right? So in the case of our circles, if we have 9 circles, right, we need to figure out, like you showed, how many times. So if we say, we could guess and say, well, is it 2 circles? No, because if we broke 2 circles down, the rest of these circles, the whole circle's down 2 times, it wouldn't equal 2. But if we broke down the circles 3 times, right, and group, then each group would be 3, and so that would be correct. So I think we've gotten somewhere.
Yeah.
If we want to go one more square up to 16, right, to show this full proof here, if we go 16, well, that's 4 times.
You need 4 more circles.
Yeah, I do. Thanks. I was like, why is this not working? It's like, why is there only 3? So that's 4 times, right?
Right.
But let's say, so this is equal to 16 square rooted. But Jaden, we also know, what is this? Do you want to draw it with your circle so we can see a different color?
Yeah, so then we know that would be...
Is it 4 or 3? 2 times 2 is 4. 2 times... Oh, it's to the 4th. Sorry.
Yeah, that would be to the 4th, yeah. So then we can get groups of 2, and we finish off with 8 groups of 2.
Uh-oh. That, because we had...
That works, right?
I'm trying to think here. Because
2
we
to
had...
the 4th is...
Yeah, wait. 2 groups of 2. We had 4... Where did we mess up here? Because I was saying that we had 4 across, and so we needed 4 down. And now we have 2. And so why is it 8? Two times 2 times 2 times 2. That's 16, right? Not crazy.
Yeah.
Okay, hold on. We're almost there. We're almost there. Promise.
It would equal... So we're looking at... If we look at the example that you circled, we'd have 16 divided by
4.
Our x is going to be...
Oh, right. Okay. Yeah, we're good.
2.
Right.
2 to the 4th? No, to the 3rd.
Right.
What? And
Which
we
is
get...
equal to 8. Or, yeah, so then
That
you get
equals
16.
2,
Yeah, okay. Well, we did it right. But maybe it's not
Okay.
as good of a visual representation as... But yeah, cool.
Yeah, it works.
It works. Alrighty. Do we want to quickly answer... What?
So the amount of groups that we end up with, so in the last situation we had 8. So this looks like 16 divided by 8. That gives you 2, which is your final answer.
Right.
For the 4th root of 16.
Right, okay, yep. How many groups equals... Yeah, okay. Alright, I can go ahead. Do we want to quickly answer Kelsey's question? Because it's not that mathematically intense. And I just did some quick research while we were talking to figure out a few things. So, Kelsey, We're going to say that our
Let me
average
read
bath...
the question again.
What?
I was just reading the question
Okay.
again.
So we're
Okay.
going to say our average bathtub contains like 100 gallons of water. That's give or take. Okay.
Okay.
A shower. Boop. Look, I get to draw this because I have blue.
Lucky.
So a shower.
Here, I'll
Oh
do the
gosh.
tub so we
Jaden,
don't
my
confuse
drawing's
with the
looking really
water.
inappropriate, I feel.
Jeez. Here.
We're gonna get
Yeah.
banned from YouTube for that one.
I'll draw the shower head really big.
Okay.
There we go.
There we go.
That's the shower head.
Okay. So we've got 100 gallons of water. There's a US regulation that Donald Trump, I don't know if he did get rid of or was trying to or what, but shower heads are supposed to have a flow of 2.5 G per minute. Okay? So,
Okay.
this is just a simple rate of change problem that if we have 100 gallons is going to be equal to 2.5 gallons per minute times X minutes, right?
I like it.
And so from there, all we do is we do 100 divided by 2.5, and this equals how many minutes? So 100 divided by 2.5 is going to be 40.
Yeah.
So it would take 40 minutes for you to fill up a bathtub that is 100 gallons with a shower head. Now, something tells me that these are larger bathtubs. My guess is, you know, a smaller bathtub is probably closer to 60 to 70 gallons. So it'd probably take
Maybe
about...
even less than that.
Yeah. Yeah, I don't know. That's what the internet told me, but I read really quickly. So, for a smaller bathtub, for us poor people out there, it probably would take, you know, about half that time. So about 20 minutes.
I just found one that says 42 gallons for the bathtub.
What? That's tiny. Well, 42. Let's do 42 just for the heck of it. Divided by 2.5 is equal to... Jane, let's do...
16.8.
16.8.
Yeah.
Cool. And look, Jaden, this is called slope.
No way. It's like we're doing a linear equation.
Yeah. Well, I guess that 2.5 is the slope, but whatevs. All right. Well, it's 8 o'clock. Thanks, everyone. Don't forget to hit that like and subscribe. We also have a donation link now, so if you just were like madly in love with our content tonight or any of the other nights, you can go ahead and donate to us. We'll get really rich, come up with better content, and save you guys the hassle of having to do your homework yourselves.
Yeah.
All right.
Sounds about right.
Stopping the streaming in 3,